Hiya! So in this video, we're going to start looking at differentiating zero forms. And basically the question we're asking here is, what's the relationship between a differential zero form and a differential one form? And in essence, the answer is that we can differentiate zero forms via differential map D to get one forms. And here I'm putting differentiate in quotes because it's a little more complicated, but in essence what we have is if we have f to be some zero form, so let's highlight that f is a zero form, and then the differential of f is going to be the one form where we basically take partial derivatives of each thing. So in other words, what we're going to do is we take the partial derivative at each component, and what we're going to do is we're going to multiply this by the derivative. xn dxn. Now here you might have come across this as being called the total derivative of f. So in other words, one forms, you can, like if you've seen this, one forms are basically generalizations of the total derivative. Because the thing is, not all one forms need to be of this form. So you can have one forms that don't look like this, but some of them will. So let's look at an example of how to get from a zero form to a one form. Let's break this down. So we're going to start off with the zero form. And we've looked at this example a couple times. So we'll kind of stick to this f where we have x squared plus y squared divided by 2. Because here we should already know these derivatives. So what's the differential of f? Let's actually go back up so we can actually see these equations. And I'll write a little to the left so you can see what I'm writing. So df here, this is again, so we have two variables, so we'll do dx plus partial f partial y dy. From earlier, what we saw is this is just x and this is just y. And so in other words, what this is just equal to is x dx plus y dy. Ta-da! That's it. So this is the one form. So it sounded all complicated and confusing, but really it's just you take the derivatives everywhere and you're good to go. Now one thing is that kind of here when we were talking about how there's this difference between total derivatives and one forms in general, this is basically the idea of an exact form, one form. So we're gonna say that the one form is exact, because this is actually like when we have a total derivative, this is kind of a nice thing. It's in some ways a nice way of getting this. So in other words, we're going to have one form be exact if there exists some zero form f such that we can get omega from f. In other words, if omega is equal to this differential of f. So yeah, so this is kind of nice. We'll stop this video here. Do I want this quick note? No, I'll say this quick note. So as an example, like in the example from before, 2.21. Where's 2.21? Can I not go back? Where's 2.21? So 2.21 is this one here. You'll notice how this omega 1 form that I had here in highlighted in yellow, omega is equal to x dx plus y dy. This was the one form. Is associated to this f, right? To the f that we just showed in this previous example. So in other words, what this is saying is this one form is an exact one form. They're not all exact, but this is life. So in the next video, we'll give a quick proposition to see when things are exact. We'll look at some examples, and we'll go from there. So I will see you in the next video for a proposition on exact one forms.